So, the next we move to the derivation of constitutive response of a compressible new Hookean elastic material. Okay. So, the hyperelastic constitutive equations that we discussed in the previous slides were general. Okay. We now focus on the compressible new Hookean material model. Okay. So, a typical form of the stored energy density function for this class of material is given by psi equal to mu by 2, the first invariant of the right Cauchy-Green deformation tensor minus 3 into mu times natural log of the Jacobian plus lambda by 2 into the square of the natural log of the Jacobian, okay, where mu and lambda are material constant and j square equal to the third invariant of the right Cauchy-Green deformation tensor. Okay. Now, as you can see, in case of no deformation, which means the deformation gradient tensor is identity. Okay. In case there are no deformation, therefore, x 1 or let us say x I will be equal to x I, where I equal to 1, 2, 3. Therefore, f, which is nothing but del x by del capital X, will be nothing but identity tensor. In that case, C will be F transpose F equal to identity. Okay. So, C will be identity tensor and J, that is the determinant of the deformation gradient tensor, will be equal to 1. And if we substitute, okay, so C equal to 1 means trace of C equal to I C will be equal to 3. Okay. So, if you substitute here, you will get mu by 2, 3 minus 3 minus mu ln 1 plus lambda by 2 ln 1 the whole square. So, 3 minus 3 is 0. So, this term goes away, natural log of 1 is 0. So, this also goes away and this term also goes away. So, which gives you psi equal to 0. So, stored energy function will be equal to 0, which means this stored energy density function can be used for a hyperelastic material model. Okay. Now, the second Pavlov-Kirchhoff stress tensor is nothing but S equal to 2 del psi by del C, and S we already have derived is nothing but 2 psi 1 into I plus 4 psi 2 into C plus 2 j square psi 3 into C inverse. Okay. And now, we have our expression for psi. Okay. We have the explicit expression for psi. Therefore, we can compute psi 1, psi 2 and psi 3. Okay. So, let us do it. Okay. So, psi 1 will be, because your psi is mu by 2 I c minus 3 minus mu ln j plus lambda by 2 ln j the whole square. So, del psi by del I c, which is nothing but psi 1 will be nothing but mu by 2, because these two terms are independent of the first invariant. Only the first term has the first invariant of the right Cauchy-Green tensor. Therefore, psi 1 will be equal to mu by 2, which is what we have here. Okay. Now, we know that psi is independent of the second invariant. Okay. Psi, so if you see the expression over here, there is no term for the second invariant, which means that the derivative of the stored energy potential with respect to the second invariant will be equal to 0. Okay. Now, the third invariant, we have the last two terms which are dependent on the third invariant of the right Cauchy-Green tensor. So, the third term psi 3 can be evaluated as del psi by del 3 c, and using chain rule I can write del psi by del 3c as del psi by del j into del j by del 3c. Okay. Now, psi is explicitly, okay. So, if you see here, psi is explicitly a function of j, therefore, the first term I can directly evaluate from the given stored energy density function. Okay. So, we have to find the first term. So, del psi by del j. Okay. So, I write again, this is mu by 2 I c minus 3 minus mu ln j plus lambda by 2 ln j the whole square. Okay. So, del psi by del j. So, the first term does not contain any j. Okay. So, that is 0 minus mu by j. So, del ln j by del j is mu by j plus lambda by 2 into 2 ln j into 1 by j. Okay. So, that is what you have here. Okay. So, if you simplify, this 2 goes away and then you have minus mu by j plus lambda by j into natural log of j. Okay. Now, let us come to evaluation of the second term on the right hand side of equation number 23. The second term is nothing but del j by del 3 c. Okay. Once we have this term, we will multiply equation 24 with that term and we will get our expression for del psi by del 3 c. Okay. So, let us see how to evaluate. We know that j square is 3 c. So, if I take derivative on both sides with respect to the third invariant, what I get? 2 j del j by del 3 c equal to 1. Okay. So, therefore, del j by del 3 c will be nothing but 1 by 2 j. Okay. So, now, if I use 25 and 24 in equation number 23, what I get? The third derivative of the stored energy potential with respect to the third invariant, which is del psi by del j, which we just evaluated as minus mu by j plus lambda by j ln j into del j by del 3 c, which is nothing but 1 by 2 j. So, once we do this, we get psi 3 as mu by 2 j square plus lambda by 2 j square ln j, the natural log of the Jacobian j. Okay. Now, we have all the three terms. So, what we do? We substitute 21, 22 and 26 in equation number 20. Okay. And equation number 20 is the expression for the second Pavlov-Kirchhoff stress tensor, and we get, so, psi by del I, which is psi 1 is mu by 2, this term psi 2 is 0, okay, and psi 3 is minus mu by 2 j square plus lambda by 2 j square natural log of Jacobian. So, this we substitute and then we just simplify, take 2 j square inside, and when we simplify, we get the second Pavlov-Kirchhoff stress tensor as mu times the second order identity tensor minus C inverse plus lambda natural log of Jacobian j into C inverse. Okay. Once we have the second Pavlov-Kirchhoff, we can obviously go ahead and compute the Cauchy stress tensor. Okay. And that is what we are going to do next. The Cauchy stress tensor can be obtained from the second Pavlov-Kirchhoff stress tensor using the following push forward operation, J inverse F s F transpose, and we substitute S from the previous slide. So, this is your expression for S. Okay. So, we get J inverse F into, this is the expression for second Pavlov-Kirchhoff stress tensor into F transpose, and we take F inside and we also take F transpose inside, and we know that C is F transpose F, therefore, C inverse will be F inverse transpose, okay, So, what we get, this expression is what we get, f inverse is nothing but identity f inverse transpose, okay, f inverse transpose f transpose, this is nothing but identity, this f inverse is nothing but identity, and f inverse transpose f transpose is nothing but identity. So, we simplify and we identify that the left Cauchy-Green deformation tensor is given by f transpose. So, finally, our expression for the Cauchy stress tensor is given by mu by j into b minus I plus lambda ln j into I. Okay. So, we can, given the deformation, we can directly compute the Cauchy stress tensor using equation 29. Okay. Now, for the purpose of numerical implementation, okay, so when you are going and implementing this material model on a computer, you need to write a finite element code, okay, and you need to develop the Newton-Raphson iteration technique. During that time, we will be needing what is called the material or the spatial elasticity tensor. Okay. So, that is what we are going to derive next. Okay. So, the material elasticity tensor is given by, and remember this is a fourth order tensor, is given by twice of the partial derivative of the second Payala-Kirchhoff stress tensor with respect to the right Cauchy-Green deformation tensor. Okay. Now, we know the expression for the second Payala-Kirchhoff stress tensor, okay, which is given here, okay, and because this expression is a function of right Cauchy-Green deformation tensor, you directly have C inverse and J is nothing but square root of determinant of C. So, your right Cauchy-Green deformation tensor is present here. So, all you need to do is take the derivative of S with respect to right Cauchy-Green deformation tensor C to get the material elasticity tensor shown by equation number 30. Okay. So, if we substitute, this is what we are going to get. Okay. So, this is what is your S. If I open up the bracket, I get twice of minus. So, the first term is independent of C. So, that does not contribute. The second term gives you minus mu del C inverse by del C plus the third term. So, this term is a function of C and this also is a function of C. So, first we have lambda ln j, lambda del by del C of ln j tensor product C inverse plus lambda ln j del C inverse by del C. Okay. So, I can now take the terms of del C inverse by del C, okay, as one term, and we get the fourth order material elasticity tensor as twice of lambda ln j minus mu del C inverse by del C plus 2 lambda del by del C of ln j tensor product C inverse. Now, if I have to explicitly get the expression for the fourth order material elasticity tensor C, then I need to compute this term over here and also need to compute this term over here. Okay. Let this term del C inverse by del C denoted by a fourth order tensor I. Okay. So, this I is del C inverse by del C. Okay. Now, I can write equation number 31 in indicial notation. Okay. Remember, it is a material elasticity tensor. Therefore, all the indices will be in the upper case. So, and it is also a fourth order tensor. So, there will be 4 indices. So, we have Cij KL equal to twice of lambda ln j minus mu Ij KL plus 2 lambda del by del Cij of ln j tensor product C inverse KL. Okay. Where the fourth order tensor I in indicial notation is given by this expression. Okay. So, we have to determine these two terms. Okay. These two terms need to be determined, so that we can have the explicit expression for the fourth order material elasticity tensor. Now, let us take this term. Okay. So, del by del C of ln j is nothing but del by del j of ln j into del j by del C. So, this is when we are applying the chain rule. Okay. And del by del j of ln j is nothing but 1 by j, and then you have del j by del C. And we know that determinant of C is j square. Therefore, if we take derivative on both sides with respect to C, we have del by del C of determinant of C equal to del j square by del C, and this is nothing but 2j del j by del C. So, this is what we want to find out. Okay. So, to find out del j by del C, we need to compute del by del C of determinant of C, and this we have already seen. This is nothing but determinant of C into C inverse transpose, and because C is symmetric, this will be determinant of C into C inverse. Okay. So, that is what we have. Okay. So, del by del C of determinant of C is nothing but determinant of C into C inverse, and determinant of C is nothing but j square. Therefore, we have del by del C of determinant of C equal to j square C inverse. Using this equation in 34, we get j square C inverse is 2j del j by del C, and from here I can directly compute del j by del C as j by 2 C inverse. Okay. Now, I have del j by del C, okay, and then I can compute del by del C of ln j as 1 by j del j by del C, and this I can substitute here. Okay. So, 1 by j into j by 2 C inverse, which is, so j cancels out, we get 1 by 2 C inverse. Okay. So, when you use equation number 36 in equation 32, you get the fourth order material elasticity tensor as twice of lambda ln j minus mu into fourth order tensor I plus 2 lambda del by del C ln j tensor product C inverse as twice of lambda ln j minus mu into fourth order tensor I plus lambda C inverse tensor product C inverse. Okay. So, this here is 1 by 2 C inverse. So, 1 by 2 cancels out, and this is what you are left. Now, we have the second term completely identified. We only are left to identify the fourth order tensor I. Okay. And this is a little involved process. So, now let us concentrate on the second term. Okay. So, in indicial notation, the fourth order tensor I is nothing but del C inverse I j by del C k l. Okay. So, if you remember from our discussion when we are discussing the mathematical basics of this course, the directional derivative of the inverse of a tensor, okay, in a general direction u is nothing but minus of A inverse directional derivative of the tensor A in the direction u multiplied by the inverse of the tensor A. Okay. Now, if I take A as right Cauchy-Green tensor C, and the general direction u is the change delta C of the right Cauchy-Green tensor, then I can identify the directional derivative of C inverse in the direction delta C as nothing but minus of C inverse delta C C inverse. Okay. And this directional derivative of C inverse in directional delta C can be written as del C inverse by del C double contracted with direction delta C, and this is equal to minus of C inverse delta C into C inverse. Okay. So, this here is what is our fourth order tensor I. Okay. But still we have this delta C which is not known. Okay. So, somehow we have to get rid of it, and for this what we do is we see that we are not able to get the final expression. So, what we do now is we write both sides of equation 41 in indicial notation. Okay. So, we write minus of del C inverse I j by del C k l into delta C k l is C inverse I k delta C k l C inverse L j. Okay. Now, if I interchange k with L and L with k on both the sides, okay. If I just interchange, I get, okay. So, I have just interchange k with L and L with k. You can see here I have interchanged. Okay. Now, I know that C is symmetric and so does the chain delta C will also be symmetric. Therefore, this C L k will be equal to C k l and delta C L k will be equal to delta L k. Okay. So, therefore, this again becomes k l and this again becomes k l. Okay. And this becomes k l. So, now I have another expression. This was the first expression. Now, just by interchanging, okay, k with L and L with k, I get another expression given by equation number 45. Okay. So, equation 42 and 45 are both same on the left hand side, and we just have I L here, we have I k here, okay, we have k j here and we have L j, okay, which means if I add equation 42 and 45 and divide by 2, I can get minus del C inverse I j by del C k l into delta C k l as this term, okay, and then delta C k l can be taken out from both the sides. So, it can be taken out and I get the expression for minus of del C inverse by del C as the average of C inverse tensor product C inverse. Okay. Now, from equation 38, I know that the fourth order tensor I is nothing but del C inverse by del C. Okay. So, this is nothing but my minus of I. Okay. So, my I is nothing but minus of this term, average of C inverse tensor product C inverse. Okay. So, finally, my expression for the material elasticity tensor will be given by C equal to 2 lambda ln j minus mu into fourth order tensor I plus lambda C inverse tensor product C inverse, where I is given by following expression. Okay. So, I can be computed. If you already know C, you can compute C inverse, and then once you have computed C inverse, your fourth order material elasticity tensor can be computed. Okay. Now, we can show that the fourth order tensor I possesses both the major and minor symmetries. Major symmetry means I j k l is nothing but I k l I j. Okay. So, I j is brought here and k l is brought here. This is called the major symmetry. It also possesses the minor symmetry, which means I j k l is equal to I j I k l and I j k l is equal to I j L k. Okay. So, here we are just in the first, we are just replacing I with j and j with I, and here we are replacing k with L and L with k. Okay. So, it can be shown that the fourth order tensor I possesses both the major and minor symmetries. Similarly, because I possesses both the major and minor symmetry, you can show that the material fourth order material elasticity tensor C also possesses both the major and the minor symmetries, okay, which are shown in equation 52 and 53. Okay. Now, we can obtain the spatial elasticity tensor by the following push forward operation. Okay. So, this relation we have already derived in our previous module, where the fourth order spatial elasticity tensor C is nothing but J inverse Fii, Fjj, Fkk, Fll into the fourth order material elasticity tensor Cij KL. Okay. And now I can substitute Cij KL here, okay, and then I can simplify to get my final expression for Cij KL. Okay. To do this, first notice this is the initial notation for the fourth order material elasticity tensor. Okay. Now, if I substitute it here, I will just have to simplify. Okay. So, that is what I do. I will substitute equation 49 in equation 54 and then I will just have to simplify. Okay. So, if I just open up the brackets, so this is the first term. Okay. So, this is the first term and then this term into this term over here, okay, gives me the second term. So, I have two terms which I have to simplify. Okay. So, this is term 1 and this is term 2 and these two terms I have to simplify now. Now, let us take term 1, okay, and then let us now substitute the expression for the fourth order tensor Ijkl from equation number 48. Okay. So, this was our term 1, okay, and when we substitute Ijkl, okay, from equation 48. So, we have minus 1 by 2 C inverse Ik, C inverse Jl plus C inverse Il, C inverse Jk, and this is the four deformation gradient tensors. Okay. Now, we know that in direct notation the right Cauchy Green tensor C is given by F transpose F. Okay. So, C inverse can then be written as F inverse transpose. Okay. So, let us now write this expression in indicial notation. Okay. Remember, C is a material tensor, which means it will have uppercase indices when written in indicial notation. So, C inverse Ij will be F inverse Ii, F inverse Ji. Okay. Now, notice we have C inverse Ik and C inverse Jl, C inverse Il, C inverse Jk. So, in equation 57, what we have to do is we have to make equation 57 consistent with these four expressions for C inverse. Okay. So, the first one is C inverse Ik. So, equation 57, if we replace J by K, then our expression for C inverse Ik becomes F inverse Im, F inverse Km. Okay. Then C inverse Jl, which is here, okay, will become F inverse Jn, F inverse Ln. Okay. Then C inverse Il, which is here, will become F inverse Io, F inverse Lo, and then finally, the last expression C inverse Jk will become F inverse Jp, F inverse Kp. Okay. So, now these four expressions for C inverse we can substitute in equation number 56. So, 58 to 61 we substitute in equation number 56 and then let us simplify. Okay. So, that is what we have substituted. Okay. So, now what we do is take these four deformation gradient tensors inside the bracket. Okay. So, we will open up the bracket and we will take these four deformation gradient tensors inside and then we will get this long expression. Okay. So, they seem to be pretty long expressions and pretty intimidating, but however, if you look closely you will find that you have Fii, F inverse Im. So, these two indicial notations have I common. Okay. Then if you see, so here you have I common, if you see Fjj, okay, and if you see F inverse Jn, you have J common. If you see FKK and F inverse Km, you have capital K common. If you say FLL and FL inverse, you have L common. Okay. Similarly, here you have FII, F inverse IO, again you have I common, you have FJJ, you have F inverse JP, you have J common, you have FKK, you have F inverse KP, you have capital K common, and if FLL, F inverse LO, you have L common. Okay. So, if you write these terms, okay, now FII, F inverse IM, okay, in direct notation, this is nothing but F inverse, okay, which is nothing but identity. So, therefore, FII, F inverse IM will become nothing but delta IM, okay, that is Kronecker delta. Okay. FJJ, F inverse Jn will become delta Jn, FKK, F inverse Km will become delta Km, FLL, F inverse Ln will become delta Ln, FII, F inverse IO become delta IO, FJJ, F inverse JP becomes delta JP, FKK, F inverse KP becomes delta KP, FLK, F inverse LO becomes delta LO. Okay. So, from equation 63 and 64, we substitute in equation 62. Okay. So, using equation 63 and 64 in equation number 62, what we get? We get minus 1 by 2 delta Im, delta Jn, delta Km, delta Ln, plus delta IO, delta LO, delta JP, delta KP. Okay. Now, again we notice that the following expression, okay, can be further simplified if we use the substitution property of Kronecker delta, okay, which means if you look delta Im and delta Km, this will become nothing but delta Ik, and delta Jn, delta Ln, this will become delta Jl, delta IO, delta LO will become delta IL, and delta JP, delta KP will become delta JK. Okay. So, further simplifying, we get our first term entirely in terms of Kronecker delta as minus 1 by 2 delta Ik, delta JL plus delta IL, delta JK. Okay. Now, we take the second term. Okay. Now, the second term is FII, FJJ, FKK, FLL, C inverse Ij, C inverse KL. Okay. Now, again I can write C inverse in individual notation. Okay. So, C inverse Ij, which is here, is nothing but F inverse Im, F inverse Jm, and C inverse KL is nothing but F inverse Kn, F inverse Ln. Okay. So, this is here. So, now we substitute these two expressions here, and then what we get? We get following expression. So, this is already there, and this comes from the first C inverse Ij, and this comes from C inverse KL. And now, we notice that FII, okay, F inverse Im will become delta Im, FJJ, F inverse Jm, that will become delta Jm, okay, and FKK, F inverse Kn will become delta Kn, and F inverse LL and F inverse Ln, that will become delta Ln. Okay. Now, in the following expression, we can again use the substitution property. So, if we look these two Kronecker deltas, this will become delta Ij because m is common, and this will become delta KL because n is common. So, finally, term 2 becomes delta Ij, delta KL. Okay. So, now if we use equation 66 and 67 in equation 55, we get our fourth order spatial elasticity tensor Cij KL as 2 j inverse mu minus lambda ln j into 1 by 2 delta Ik, delta JL, delta plus delta IL, delta JK plus j inverse lambda delta Ik delta ij delta kl. Okay. So, this 2 cancels out, okay, or we can write this itself as a 4th order tensor I. Okay. That is the 4th order identity tensor I. So, in that case 2 will remain, and then in direct notation I can write my 4th order spatial elasticity tensor C as 2 by j mu minus lambda ln j 4th order identity tensor I plus lambda by j and tensor product of 2nd order identity tensor I. Okay. Now, where we can treat this I, okay, that 4th order identity tensor as the push forward of the 4th order tensor I. Okay. So, this I is the push forward of capital I, okay, and in initial notation this is given by following expression. Okay. So, Iij is nothing but Fii, Fjj, Fkk, Fll, Ijkl equal to 1 by 2 delta Ik, delta Jl, delta Il, okay, delta Jk. Okay. So, now we have shown that the spatial elasticity tensor we have just derived is similar to one which is used in linear elasticity. Okay. So, what it means is the spatial elasticity tensor that we have derived here under special condition will give you the 4th order elasticity tensor that is usually used in linear elasticity. Okay. So, let us see how that can be done. Okay. So, remember in initial notation the 4th order spatial elasticity tensor is given by following expression. Now, let us say we denote mu lambda ln j by j as mu dash and lambda dash as lambda by j. Okay. So, this becomes lambda dash and this term over here. Okay. Okay. So, now this term over here becomes mu dash. Okay. So, then we can writeCijkl as mu dash delta Ik delta Jl plus delta Il delta Jk plus lambda dash delta Ij delta Kl. Okay. Now, suppose you are dealing with small strain, and that is what linear elasticity means. Linear elasticity means your deformed and the undeformed configurations are very close to each other, which means the that the deformation gradient tensor F is nearly equal to identity. Okay. If F is nearly equal to identity, this implies that the Jacobian, which is nothing but determinant of F, okay, determinant of deformation gradient tensor F is nearly equal to 1. Okay. If j is nearly equal to 1, it means ln j nearly becomes 0 and this j is nearly equal to 1, which means mu dash will be equal to mu, and lambda dash, because j is nearly equal to 1, then lambda dash becomes equal to lambda. Okay. Now, if you substitute this both here, okay, then we get the 4th order spatial elasticity tensor as mu lambda delta Ik delta Jl plus delta Il delta Jk plus lambda delta Ij delta Kl. And now, here mu and lambda are your Lemmy's, okay, constant. Okay, they are Lemmy's constants, and then if you recognize this equation over here, equation 74 has the same form as that used in linear elasticity. Okay. So, the new Hookean material model under very small strain is similar to linear elasticity. Okay. So, that is what we have written here. Equation 74 is nothing but the expression for elasticity tensor used in linear elasticity. Okay. Now, we notice that the 4th order spatial elasticity tensor C possesses both the major and minor symmetries. Okay. So, it can be easily shown that the spatial elasticity tensor possesses both the major and minor symmetries which means that Cij KL equal to CKL Ij, that is the major symmetry, and Cji KL is Cij Lk. Okay. That is the minor symmetry. Okay. So, these major and minor symmetries help you to reduce the number of independent elastic constants. Okay. Now, let us see one example. Okay. So, now consider the case of a simple shear which is given by x1 equal to capital X1 plus A into capital X2, small x2 is capital X2, okay. X3 is capital X3, and where A is a scalar value. Okay. So, this is simple shear. So, you can identify this if you have a block. Okay. So, you have a block of certain length, say L, and if you apply this simple shear, okay, so what will happen? It will deform something like this. Okay. So, this will become A times, okay, if say this is equal to L, let us say a square, this will be A times L, and this will go here, and this will be nothing but your L plus A times L, which is 1 plus A L. Okay. So, this point coordinate becomes A L into L, and coordinate of this point becomes 1 plus A into L comma L. So, there is no deformation in the second direction because x2 is capital X2, and there is no deformation in the third direction because x3 is capital X3. Okay. Now, if you have a new Hookean material model, you have to determine, you have been asked to determine the expression for the pressure P. Okay. So, how do you start? The first thing we have to do is, you have to compute the, so let me rub this. So, the first thing you have to compute is the deformation gradient tensor F. Okay. So, deformation gradient tensor is nothing but del x1 by del capital X1, del x1 by del capital X2, del x1 by del x3, okay, del x2 by del x1, del x2 by del x2, del x2 by del x3, del x3 by del x3, okay. So, del x3 by del x1, del x3 by del x2, and del x3 by del x3, okay. And you have been given small x1, small x2, small x3, which is the spatial coordinates in terms of the material coordinates x1, x2, x3. So, del x1 by del x1 is nothing but 1, del x1 by del x2 from this is A, and rest or 0. Similarly, this term is 0, and del x2 by del x2 is 1, del x2 by del x3 is 0, del x3 by del x1 is 0, del x3 by del x2 is 0, and del x3 by del capital X3 is equal to 1. So, once you have the deformation gradient tensor, okay, you can compute the Jacobian. Okay. If you compute the Jacobian, if you take the determinant of F, you see that the Jacobian is equal to 1, which means a simple shear is a isochoric deformation. Okay. So, next you can determine the left Cauchy-Green deformation tensor, which is nothing but B and is equal to F into F transpose. We already have computed F. So, we can compute F into F transpose, which is nothing but 1 plus A square, A 0, A 1 0 0 0 1. Okay. So, now once you have the left Cauchy-Green deformation tensor, I know my relation for the Cauchy stress tensor, and the relation for the Cauchy stress tensor is given by following relation: sigma equal to mu by j b minus I lambda ln j into second order identity tensor I. Okay. So, remember j is equal to 1, therefore, ln j will be equal to 0. So, this term will drop out, okay. And I have already computed b. So, I can substitute b and I can simplify, okay. So, we substitute for b, okay, and j, and we can get the Cauchy stress tensor as sigma equal to mu times a square a 0 a 0 0 0 0 0, that is your Cauchy stress tensor. Now, pressure is nothing but, okay. So, pressure is nothing but trace of sigma by 3, okay. So, I can take the trace is nothing but sum of the diagonal component, which is a square plus 0 which is nothing but a square divided by 3. So, pressure will be equal to a square by 3, that is our answer, okay. We can also note that as a approaches 0, we get what is called pure shear, okay. So, with this example, you could see that as soon as you are given the deformation mapping, you can compute the deformation gradient tensor f. In the finite element context, you will be given the deformed coordinates, okay, and using the deformed coordinates and the initial coordinates, you can determine the deformation gradient tensor f, okay, at a particular Gauss point. Once you have determined the deformation gradient tensor f, you can determine the Jacobian, which is nothing but the determinant, okay, and also you can determine b, the left Cauchy Green deformation tensor, which is nothing but b equal to ff transpose. And then using the relation for the Cauchy stress, you can directly compute the Cauchy stress tensor by substituting for left Cauchy Green deformation tensor b and the Jacobian j, okay. And once you have substituted, you will get the Cauchy stress tensor at a particular Gauss point. Once you have the Cauchy stress tensor, you can compute the internal forces, and once you have the internal forces, you can calculate the residual which is required for the Newton-Raphson iteration, okay. So, the next example that we consider is as follows. So, you consider a deformation mapping, okay, at a material point 1 1 1, okay, as is given here, okay. Now, considering a new Hookean material that we have derived constitutive relation just now with the strain energy density potential with the material constants mu and lambda given by 2 and 3 respectively, okay. With this information in hand, you have to find the Jacobian of deformation, the first invariant of the Cauchy stress tensor, and the third invariant of the stress tensor, okay. And also you have to find the hydrostatic pressure, okay. So, the significance of this problem is the steps that will carry out to find out A, B, C and D are exactly what we need to implement inside a finite element code, okay. So, the first thing when you have a mapping, okay, is to find out the deformation gradient tensor, okay. So, for the first solution, you have to find out the deformation gradient tensor, and that is given by del x1 by del capital X1, del x1 by del capital X2, del x1 by del capital X3, del x2 by del x1, del x2 by del x2, del x2 by del x3, del x3 by del x1, del x3 by del x2, del x3 by del x3, okay. So, now from this deformation mapping, you have been given x1 as a function of material coordinates, x1, x2, x3, and although not shown here, this deformation mapping may also be a function of time, okay. So, you have x1, x2, x3 material coordinates and time possibly, and x3 is a function of x1, x2, x3 and time. So, suppose you were given a problem where there was also a term containing time, okay, or the time was explicitly present in the deformation mapping. At that time, you would be asked to find out all these quantities at a particular time t equal to t0. For example, you might be given t0 equal to 1 second, okay, or 1. So, at that time t equal to 1, and for a material point say 111, you need to find out all these values. Okay. So, first thing is you find out this deformation gradient tensor, and this deformation gradient tensor, okay, you can see will be del x1 by del x1, which is 4 minus x2, then del x1 by del x2 will be minus 5 minus x1, then del x1 by del x3 is 0, because this term is independent of the third spatial direction x3. So, this is 0. Then you have del x2 by del x1, del x2 by del x1 is 2, del x2 by del x2 that is equal to 1, del x2 by del x3 equal to 0, del x3 by del x1 0, del x3 by del x2 0, and del x3 by del x3 equal to 1. Okay. And now you have been given the material particle. Okay. So, the material particle or a position at 1 1 1. So, you have to evaluate this at 1 1 1. Now, if you are given time, also you would have to evaluate this at that particular material particle at that particular time instance t0. So, you have to both substitute the material point as well as the time t. Okay. Now, if you substitute, so you have been given x1 as 1 and x2 as 1. Okay. We do not require x3. If you substitute x2 as 1 here, you get 3. If you substitute x1 as 1 here, you get minus 6, you get 0, okay, you get 2, 1, 0, 0, 0, 1. Okay, that is your deformation gradient tensor. So, once you have the deformation gradient tensor, you can compute the Jacobian. So, the Jacobian is given by determinant of f, and you can compute the determinant of f, which comes out to be 15. Okay. It will never be this high in actual situation, but this is a hypothetical case. So, say it is that high of 15. So, the first point is solved. Now, we need to find out the first invariant and the third invariant of the Cauchy stress tensor and the hydrostatic pressure, and all these three invariably depend on the Cauchy stress tensor. Okay, they have to be derived from Cauchy stress tensor. So, what we need to first find out is the Cauchy stress tensor, and for a compressible Neo-Hookean material, we have already derived the expression for the Cauchy stress tensor in terms of the left Cauchy Green deformation tensor B. B is given by F transpose. So, we have already calculated F here. Okay. So, the next thing is we compute the left Cauchy Green deformation tensor, and which is given by P equal to F transpose, and when we compute this, we get 4500 050 000. Okay. Once we have computed the left Cauchy Green deformation tensor, we can compute for this Neo-Hookean material the Cauchy stress tensor from this particular equation, where mu and lambda are the material constants which are given to us. Mu is 2, lambda is 3, j we have already computed. Okay. So, j was, so this is 3, j was 15, I is a second order identity tensor. Okay. So, this will be 100 00 100 010 001. Okay. And B is here. So, all we need to do is just substitute all these values here. So, will be 2 by 15 in the bracket 45 00 050 001 minus 100 010 001, okay, plus 3 times natural log of 15 into 100 010 001. So, once you do this, you will get the Cauchy stress tensor as a 3 by 3 matrix. You will get all the 6 components. Okay. So, once you do this, you get all the 6 components as 6.4083, 0, 0, 0, 1.0749, 0, 0, 0, 0.5146. So, now you have the Cauchy stress tensor, and now the 3 parts that we have to evaluate are nothing but the first invariant, which is nothing but the trace of sigma, which means it is the sum of the diagonal components. The third invariant is nothing but the determinant of the Cauchy stress tensor, and because this matrix is a diagonal matrix, then the determinant is product of the diagonal term, and the pressure is nothing but the trace of sigma divided by 3. Okay. So, the first invariant is nothing but trace of sigma, and which comes out to be 8.0248. Okay. The third invariant is nothing but the determinant of sigma, which is the product of the diagonal component, because our sigma was a diagonal matrix, and this comes out to be 3.7309. Okay. And the pressure is now evaluated as trace of sigma by 3, which is the first invariant divided by 3, which is 2.6749. Okay. So, in a similar way, when you are coding in a finite element setup at every Gauss point, okay, so what will happen in a finite element code, instead of that material point, you will have to take the Gauss point coordinate, and at time you have to take that particular instance of time when you have to compute all these quantities. So, the way you will approach is from the coordinates, you have to first find out the deformation gradient tensor f, then you check or you compute the Jacobian j, and you check for whether Jacobian is less than a certain small number, and then you go on to compute the Cauchy stress tensor, and you compute all the quantities. Okay. You also have to compute the internal force. That is what we will discuss in the next module. Okay. So, with this we come to the end of this module. In next module we move to linearization of the equilibrium equation and taking the directional derivative of the principle of the virtual works expression, which will be essential for getting the tangent matrices for setting up the Newton-Raphson iterative procedure. Okay. Thank you.